Today's class is about assigning oxidation numbers. We're going to review the rules of how to attribute the oxidation state of a particular element. They're fairly simple rules, and they'll become simpler if you do a little bit of practice, which we'll do on the next board. Elements in their elemental form have an oxidation number of 0. So for example, if you have elemental sodium, metallic sodium has an oxidation state of 0. Metallic iron has an oxidation state of 0. Gaseous oxygen has an oxidation state of 0, and so on. The oxidation number of a monatomic ion is the same as its charge. So if you have sodium with a +1 charge, that's the oxidation state of the sodium. The third rule is that nonmetals have negative oxidation numbers, usually, not always. There are examples where they'll vary. Oxygen is usually -2, except in peroxide where it's -1, and in superoxide it's -1/2. So it's also possible to have non-integer oxidation states. Not as common, but it is possible. See, O2, oxide is -2. O2 with a -2 charge is peroxide, so each one of the oxygen atoms is a -1. And if you have O2 with a -1 charge, which is called superoxide.
Excuse the interruption. Mr. Renault, please report to Moen Hall. Mr. Renault to Moen Hall.
And superoxide, which is 2 oxygen atoms with a -1, will give you half, -1/2 each. Hydrogen, because it's in the middle of the electronegativity series, will be -1 when it's bonded to a metal, because metals are way less electronegative than hydrogen, and it'll be +1 when it's bonded to a non-metal. So if you take hydrogen fluoride, for example, the oxidation state of hydrogen in that case is +1. If you take sodium hydride, the oxidation state of hydrogen in that case is -1. So depending on what it's bonded with, it acts in different ways. Fluorine is always -1. Other halogens are normally -1, except in oxyanions, where they can have positive oxidation numbers. We'll see several examples of that later on. In a neutral compound, the sum of the oxidation numbers is 0. So for example, calcium oxide, the sum of the oxidation numbers is 0 because calcium is +2, oxide is -2. In a polyatomic ion, the sum of the oxidation numbers is equal to the charge on the ion. So for example, perchlorate anion has an oxidation state of -1, but it's composed of oxygen, which the oxygens are -2 in it, and the chlorine is actually +7. Now we'll see several examples worked out here on how to attribute the oxidation state of different elements. Lithium in its naturally occurring state is 0. The lithium cation is +1. Calcium oxide, we have calcium with a +2 charge, oxygen with a -2 charge. So rule number 2 says that the oxidation number of a monatomic ion is the same as its charge. So its oxidation state is +2. The oxidation state of oxide is -2. In sodium hydride, sodium has a +1 charge, therefore hydrogen is a -1 charge. Overall it's neutral. In water, the hydrogen is +1, the oxygen is -2. You'll notice the 2 hydrogens each at +1, to the 1 oxygen at -2. In peroxide, the hydrogen is still +1, but the oxygen is -1 each. In fluorine, which is a diatomic element, the oxidation state of fluorine is 0. That's its naturally occurring state. But in hydrogen fluoride, it is +1 for the hydrogen, -1 for the fluorine. In perchlorate, we see that the overall charge on the ion is -1. Each oxygen atom is at -2, but the overall is -1. So where is the +7? It's got to be the chlorine. The chlorine is in its +7 oxidation state. Whereas in chlorate, with 3 oxygens each at -2, you would expect the overall charge on the anion to be -6, but it's only -1. So something has to be +5, and in that case it has to be the chlorine, which is at +5. In the chlorite anion, there are 2 oxygens each at -2, but the overall charge is -1, which means something has to be +3, and that would be the chlorine. And in hypochlorite, we have -2 for the oxygen and only +1 for the chlorine. So you see the chlorine runs the gamut of possible charges from the -1 all the way up to +7. Here's another example with ferric oxide. In this one, the overall charge is 0. It's an ionic compound. Each of the oxygens are -2, so you have a total of -6 charges. So if something else is +6, it has to be the ferric ions, each one of them are +3, so 2 times +3 gives you the +6 that you're looking for, so overall it's neutral. The next step, we're going to learn about Voltaic cells. In spontaneous redox reactions, electrons are transferred and energy is released. We can use that energy to do work if the electrons flow through an external device, like a wire. So for example, if we run the electrons through a very thin tungsten wire, the friction of the electrons running into the tungsten atoms causes them to get very hot, and the tungsten filament will glow white hot. And of course, because tungsten has a very high melting point, it doesn't melt, so it continues to glow white with heat, and it makes the perfect means of lighting up a room. We can also run those electrons through a heating element so that the element gets red hot, and you can use it to cook your food. Or you can run those electrons through a wire that have been wrapped around a coil, and the coil will generate a magnetic field which will cause something else to spin, and that's how we make electric motors, and so on. So the energy contained by these electrons moving through a wire can be harnessed. And this is the basis of 20th century technology when it comes to using electricity. We have solenoids, and we have motors, and we have heating elements, and various other applications that use combinations of all those other things, as well as electronic circuits. So in a voltaic cell, reduction occurs at the cathode, meaning that something positive is attracted to the electrons that are present in the cathode. And so, for example, if you have a silver cation, it will be attracted to the cathode. It will take the electrons from the cathode and become metallic silver, and then deposit onto the cathode. The salt bridge in a voltaic cell keeps the charges balanced, because as you remove cations from the solution, you will now develop a charge imbalance, because the chloride anions that might be, or maybe not, you wouldn't use chloride for silver. Supposing you had nitrate anions floating around the solution, when you start removing the silver cations, now the nitrates are in excess. Where are they going to go? Well, you put a bridge that connects to the other cell, and they can work their way over to the other side, helping to keep charge balance. If you don't have charge balance, the reaction will stop occurring because of the buildup of charge. So cations move towards the cathode, anions move towards the anode. Anions are negative, cations are positive. So that's one of the things you should remember. In fact, I joke with my students that the only thing I know about electrochemistry is that electrons move from the anode to the cathode, A to C. Everything else can be reconstructed, as long as you remember that one fact. Electrons move from A to C. Everything else you can make up, and from this one fact. So, as the electrons leave the anode, the cations that are formed dissolve into the solution in the anode compartment. So what happens? Where are the electrons coming from? They're coming from the anode, and to do that, what has to happen is the metal has to leave the anode and go into solution in the form of an ion. So it leaves behind these electrons, and the electrons then move their way up the wire to the other side of the cell where the cathode is. And that's where these extra electrons are coming from. As the electrons reach the cathode, cations in the solution are attracted to the now negative cathode, which is what we explained here at the very beginning. Electrons are taken by the cation, and the neutral metal is deposited on the cathode. So the cathode tends to get heavier as the reaction proceeds, whereas the anode on the other side of the cell tends to get lighter because it's losing metal. Electrons flow from higher potential energy to lower potential energy. And what we deem to be higher potential energy is something that has a positive voltage. When the voltage is positive, it means it'll push out the electrons. And so the electricity flows from anode to cathode. The peculiar thing is that you have a higher concentration of electrons in the cathode, but it's labeled as positive. The red wire is labeled as positive, whereas the black wire is labeled as negative. So that can be confusing for some students. Just think of how the electrons are flowing from the anode to the cathode, and it'll help clear up that confusion. So water will flow from a higher energy to lower energy. Recall that the higher energy electrons are the ones that are listed as having a positive potential. Let's stop it there.